Oh, that's loud. Lesson 3, we're going to do function operations, and then at the end, we're going to do something that's called composition of functions. So first, let's start with function operations. We're going to see how we can obtain new functions from other functions by the means of arithmetic operations like addition, subtraction, multiplication, or division. So basically, we're going to add, subtract, multiply, divide the functions, equations, the f of x, g of x's, the y's of the function to get new functions. The domain and the range resulting from these operations will definitely be dependent on the original function's domain and range. So for example, if we're just adding two linear functions, the domain and range won't change. But if we're adding a linear function with a quadratic function, we might have to look at a change depending on those new functions. So, or when we divide functions, then we have to restrict domain because we're going to divide by a function and we cannot divide by 0. So we have to make sure that we exclude those values from the domain. So we will go over those situations together. Now let's have a look at new functions, equations, and how we can obtain them. And you have some notes here for that. For sum and difference, so addition and subtraction of functions, let's call the new function. So this is the new function. Let's call it h of x. We're going to get a new function h of x by adding two other functions. One is f of x, the other one is g of x. You can write it like this, f plus g of x, or you can just write it separately like this, f of x plus g of x. And subtraction is exactly the same way, but with subtracting a sign. And then again, you can write it two ways, either f minus g of x, or you can write it separately as f of x minus g of x. They mean the same thing, just different notations. And then product and quotient of functions. So product is going to be f times g, or f of x times g of x. And quotient is going to be f divided by g, or g divided by f, depending on the question is asking you to do. Now, this is what the situation where we're going to have to be careful, because when we divide by an expression, and functions are going to be expressions that involve usually an x or a variable, we want to make sure that we don't divide by whatever value it is that's going to make it 0. So for that reason, for these functions, we always have to consider this condition. So condition. And we're going to make the condition that the g of x, whatever the expression is, cannot be 0. We will definitely go over this one in detail, so don't worry about it just yet. Now, graphically, when we have to obtain our new functions, the easiest way to get to the new graphs is by remembering that these notations, the f of x and the g of x, refer to the y coordinates or the y values of the functions if you know the x of the input. And you will know the input because you will be looking at graphs in some questions. So imagine this, let's say here, let y1 equals f of x, and let y2 be g of x. So these ones, remember, we just say either we say f of x or g of x, or we use it with the y notation. It doesn't really matter. Then if I do the sum of two functions, all I have to do on the graph is add y1 with y2 for the corresponding x. If I would do difference or subtraction of functions, you would do y1 minus y2, or the other way around, depending on the question. If I do product, you do y1 times y2. If you do quotient, For the allowed values, of course, you would do y1 divided by y2. Okay, y2, it cannot be 0. That's what we're going to do when we get to graphing. And for all of these, x is the same. So we keep the x the same value, and then we just add, subtract, multiply, divide the corresponding y's of those points. So first, the first example, we're going to go through writing equations of these new functions. Consider the function f of x equals 2x plus 1 and g of x is x squared. Determine the explicit equation. Explicit meaning we're going to have to simplify it if there's any like terms of each of the functions below. So first one is h of x. It's going to be the sum of f and g. So I like, again, to write it with the separate notation, f of x plus g of x. F of x is 2x plus 1. So you're just going to write that 2x plus 1 there. Plus g of x is x squared. So we added a linear function with a quadratic function. What new function did we get, linear or quadratic?
Quadratic?
That's right, quadratic, yes, because we have the highest exponent squared now. Now this is an okay equation, but with polynomial functions, we usually write them in a descending order of exponents. So we're going to rewrite this one as x squared plus 2x plus 1. So that's the new function called h of x. So a linear plus a quadratic will result in a quadratic. And you can even give yourself more detail here. A positive leading coefficient linear with a positive leading coefficient quadratic is going to give you a positive leading coefficient quadratic. So you can even imagine the graph is going to be upwards, or look at the equation. But when you don't have the equation, this thinking helps. Any questions for 1A? Moving on to subtraction. Now, careful with the subtraction of functions because order matters. Just like when you say 3 minus 5 or 5 minus 3, the two different operations with two different answers. So in this situation, we are going to subtract from f of x the function g of x. So f of x is first, g of x is second. So f of x, again, the same, 2x plus 1, and then minus x squared. So notice we have a negative x squared plus 2x plus 1 as our final equation. So when you have a linear function plus a negative leading coefficient quadratic, you're going to get a quadratic with a negative leading coefficient, which is going to be like that. So after each part, A, B, C, if you have any question, please interrupt me. I'm going to keep going until the very end now. So I of x is obtained by doubling the function f, so adding f to itself. So f of x plus f of x. So we have a linear plus a linear. We're going to get what kind of function? Linear, right? Linear plus linear, we're gonna get another linear. So 2x plus 1 plus 2x plus 1, here we have like terms. So we have 4x plus 2. This has a bigger slope, so it's going to be a steeper line in comparison to f of x. So basically this one is the same thing like you would do 2 times f of x, right? Doubling the function, the same thing. So it will be a vertical stretch by a factor of 2, if you want to look at it from the perspective of transformations. J of x. We have g minus f of x, so g is x squared minus, now you're gonna have to be careful because f of x is a binomial. So you have to open the bracket here because you're gonna have 2x plus 1. Both of those terms have to be subtracted because both of them are part of f of x. That one has to be always known. When you're putting a negative in front of a binomial, you gotta apply the negative to both. So we have x squared minus 2x minus 1.
Sorry, can you say that again? Can you like explain that part again?
When we're subtracting two expressions and then the expression after the negative has multiple terms, so this one has 2 terms, it's called a binomial. You either know that the negative goes to each, or you put brackets so you can see why that happens, right? Because you're basically negating everything that you're putting after. But if you forget the bracket, then your answer will be incorrect at this location. So negative 2x and negative 1. It has to be distribution. Make sense?
Yes.
Okay. In the last one, we're going to do the multiplication, and we're going to leave the division for later on when we discuss domain and range. So we have f of x times g of x. So a linear times a quadratic. What do you think you're going to get?
Cubic.
Cubic, that's right. So we have 2x plus 1 times x squared. So we have 2x cubed plus x squared. So that's how you get equations. You just basically applying those operations onto the function's equations. Again, this is probably the type of that you have to be really careful. Okay, so if you're subtracting something that has multiple terms, you got to be careful with the distribution there. Let's do values. This time we're just focusing on finding the corresponding function values for the new function without going through the equation. Yes, you could find the equation first and then find the value, but it's a little bit too much work. This is actually the work we are doing for graphing. So this is the work for graphing as well. Because what we're doing, we're finding the individual y values for the given x, and then we're going to just apply the operation. So example 2 says, consider the functions f of x equals square root of x minus 1 and g of x, x minus 2. Calculate the exact value. So you're looking for a value, which is a number of h of 1. So h is the new function. The new function with the input of x1 And then we have to obtain this new function, f plus g. That's what we have to do. But again, we don't want to work with equations. We're just going to go straight to the value. So the function h is going to be obtained by doing addition of the functions f and g. And then if I want a function value at x equals 1, all I have to do is work with f at 1 and then with g at 1. These are just the y values of these functions where x equals to 1. Let's do that. Let me just highlight for this first example so it's clear what we're doing. First one, f of 1 means just take x1 and plug it in where you have an x in the function f equation, so square root of 1 minus 1. That's how you calculate f at 1. Plus, now g of 1 means take the 1 and plug it in everywhere you see x in the function g, so 1 minus 2. Put a bracket here so you understand that binomial. You don't have a negative here, but you always have to be careful with binomials that come after operations. Okay, so now we're just going to calculate square root of 0 plus 1 minus 2 is negative 1. Square root of 0 is 0, minus 1 is negative 1. Right? So this is the y1 of the first function. This is the y2 of the second function. What's the x for this function? And for the new function h? X equals 1. So you basically would have points for function f. You would have the point at 1, 0. And for function g, you would have a point at 1, negative 1. And all we're going to do for graphing is take that y with this y and apply the operations. And that's what we're doing here, just doing it algebraically. And we get our new point, right? Our new point on the function h is going to be 1, negative 1, right? Give you a moment there. Maybe you have a question. If not, we'll move on.
So x equals 1 because our final answer was negative and we flipped the sign.
No, x plus 1 because it's part of the question. So it says
Okay.
calculate h of 1. So this is the corresponding notation for h of x, but now you know what the x is because it's given.
Okay.
That's why x is 1 here.
Okay.
So the next one. So we're calculating the function value for the function k at 0. So that means we're calculating for x equals 0, right? So we're doing subtraction of f and g. So we're going to do f at 0 minus g at 0. Now f at 0 is going to be square root of 0 minus 1. And then minus g at 0 is going to be 0 minus 2. Now, here I'm going to end up with something, but here I can calculate it, which is 0 minus 2 is negative 2. Now, here I'm going to end up with square root of negative 1. And I run into a problem. Not defined. Okay, it does not exist, whatever you want to name it. Not defined does not exist because we cannot calculate square roots of negative numbers, right? So when you have situation like that, there's no corresponding value for this function. So no value, no value, no point on the graph. Because what happens for the f at 0, you don't have a point for that function. So there's no point to actually work with that has x equals 0. Or in other words, the value 0 is not part of the domain of the function f. So you can't work with it. J at 4. So the x equals 4. We're doing g at 4 minus f at 4 equals g at 4. 4 minus 2 minus f at 4. Square root of 4 minus 1. That's 2 minus square root of 3. And we can just leave it alone. Now, those of you that are using calculator extensively, you might be tempted to evaluate that to an approximate decimal. Don't, just leave it as an exact value, especially because most of our questions will say exact value. That's what they refer to. Sometimes we learned so many new terms in this course that this might get you into trouble. You may think it's something special. It's nothing special. It just wants an actual number value. And you end up with a fraction, you leave it as a fraction. You end up with the root, you leave it as a root. Now, for the graphing purposes, yes, you will have to evaluate it on the side, so you can see what that means. But for questions like these, no. The function L at 10. I hope you're getting the pattern of these ones. And you know how to, you're always going to get a question like this in the test with values and equations. So f at 10 times g at 10. F at 10 is square root of 10 minus 1 times g at 10 is 10 minus 2. Square root of 9 times 8. That's 3 times 8, which is 24. And last one, when x is 5, from function n obtained by the quotient of g and f. So we have g at 5 divided by f at 5. G at 5, 5 minus 2, f at 5, square root of 5 minus 1. It's 3 at the top, square root of 4 at the bottom, 3 over 2. Your turn. We're going to skip that, let you work on it a little bit later at the break time. Let's go to sketching. Now for Your notes, I only have the same graphs, 2 linear graphs, but in your practice questions, you have a variety of other types of graphs. So make sure you go through your practice questions so you can see how your new functions may look like. But the main thing is that all of the steps are the same. So doesn't matter which functions you're working with. You can always analyze what type of functions you end up with. So theoretically speaking, for example, when we're doing addition, so we have a linear plus a linear, we're gonna get another linear, right? We already seen that in the equation. If I would have a linear times a linear, I will get a quadratic. So I'll know that I will get a parabola, right? So it's a really good idea to write for yourself what you're gonna get so you can imagine how to connect the points that we will obtain. Now, when we are sketching new functions that are obtained by operations of functions, we're gonna remember that when we do f of x plus g of x, this just means the corresponding y value of each of these functions added together, okay? Now to keep organized, we will be doing this work in a nice little table just to keep track of our work. It's nice and neat. In the first column, I'm gonna put x. So it's gonna be the x of our choice that we're gonna work with to get values. And then in the second column, I'm going to put the functions in order, in the order that matters. In this case, the order doesn't matter, but I always like to keep it in the same order. So f of x, so the value that I'm looking for, the y1. In the third column, g of x. And in the last column, f plus g. And in this is the last column, but I also like to put down here points at the very end. Okay, so let's make a few rows. So this is going to be giving us a linear function. We don't need that many points, but I will probably do a few of them with you so everybody understands the process, okay? Now, for these ones, because we are working with y's of the functions, the ruler has to stay horizontally or vertically. What do you think? To help you visualize it better.
Vertically.
Vertically, right? So we are choosing a certain x, okay? So for example, I'm going to choose -4 because the ruler is at -4. So I'm going to take note of it, -4. And then I'm going to mark, making sure that I know where the points of each of my function, the function f of x is this one, the function of g of x is that one. On each of my function, I know the points that I'm going to be working with, but I only need the y coordinates because the x stays the same. So the y coordinates for the function f for x equals -4 is going to be -5. So I'm going to write it here, -5. And then for the function g, it's at 5. All we have to do is add them. We already got them, add them. -5 plus 5 is 0. So the point is going to be this -4 from here with this y from here. -4, 0. So this is the y of the new function. And you can plot them if you want right away, or just wait to get a few points that you need and then unite them. Again, this is going to be a linear function, so we only need a few points, a couple of them actually, and then from there on it's just extra. So -4, 0 is right there. Now let's choose another one. Who wants to go for it? Anyone?
Sorry, quick question before you move on. How did you get the numbers?
From the y coordinates of the points. So see how I chose -4 here? If I go from here to the function f of x, I will run into the point that has that x coordinate. So this point right there has -4 as the x, and then the y is -5, right? On the function g, I'm going to run into this point with the x coordinate -4, and then the y coordinate is right there on the right-hand side, so it's 5. All we got to do now, once we figure out the 5s and the -5s, is take them and then add them together based on the rule, because we're doing the addition of functions. We're good?
Yeah.
Okay, so now once we got that value of the addition, that's the y coordinate of the new point of our new function. So let's keep going, because this is going to be the same thing over and over. So by the end, hopefully,
question.
Yeah.
Should we be labeling these points?
no, not for this
Okay.
type of question. No, it's going to be a bunch of like letters, and for a linear function, you need 2 at least. But for a quadratic or a cubic, you might find yourself you're finding, I don't know, 10 points, and then you're going to have 10 letters too many, you know. Okay, so who's going to choose our next x?
What about +4?
+4. Okay, let's see. +4. So the function f point is right there. And the function g is right there. So you read that, which is 11. And then -3. And then 11 minus 3. Or plus minus 3, whichever you want, but we get 8. Point is 4, 8. 4, 8. Right there. So basically now I could be graphing my my function, but we can do a third and a fourth just to make sure that whatever points we're getting, they're going to be collinear, right? They're sharing a line. Because if you're getting somewhere else, then something is wrong when you're expecting a line. Okay, so somebody maybe here in between, another one, just to confirm.
0.
0, sure. So 0 is right there. There's the function f. There's the function g. So when x is 0, function f is got 3. And function g is at 1. 3 plus 1 is 4. 0, 4. There's our line. Is it clear for everyone how you're getting the graphs of functions through operations?
Where did the 8 come from? The point.
This one from here,
Yeah.
that's our second option
Oh, right. Okay.
at 4.
Right.
The f of x is 11, g of x is -3, so we got the 8. Let's do subtraction. We're going to use the same function, but we're going to choose different x.
Can you please go back? I'm trying to graph the one in blue.
As you guys are finishing up your graphs, I will set up my table again, exactly the same headings. So those of you that are ahead, you can do the same too.
Yeah, I'm done.
Good job. So let's do our table for the next question. It's exactly the same graphs. We're just going to go through now with subtraction. So we're going to do f of x minus g of x. You have to be careful with subtraction. Always do it in that order, because if you switch the order by accident, then here you're gonna get a different answer. So f minus g there, that's the point. And this is our selection of x's. So I'm gonna start the first one with the -3, because we haven't chosen -3 yet. -3, so exactly the same process. At -3, function f is at -3 as well. Right there, -3, read it. And the function g is at 4. So -3 minus 4 is -7. So -3, -7 is the point. -3, -7, right. Okay, so I've done the first one. Now you're going to choose the other values. So not -4, not 4, not 0, not -3. Other x's that we can work with and do the subtraction.
1.
1. That's perfect. 1. And we have f at 1 is 5. And then g at 1 is 0. 5 minus 0 is 5. 1, 5. So our graph, since it's going to be a linear function, it might look like that. We just need maybe an extra 1 or 2 points. Just confirm they're going to be collinear. Okay, somebody else, another x value. Did you say 3?
Yes, 3.
3. So f at 3 is 7. G at 3 is -1. Now here we're going to have to pay attention, right? Because we're doing subtraction of a negative. 7 subtract -1 is 7 add 1. So 8. 3, 8. 3, 8. Let's see. Are they aligning? They sure are. Do you want to try one more? Maybe this time you can tell me every single one of these answers.
How? I think you put your last point in the wrong spot, no? Because it's at 2, not 3.
Is it at, did I put it at 2?
Yeah, you did.
2,
3.
3, 8. 3, 8. And then something is wrong then? 3, 8, or do they still align? That's not possible. 3, 8. Maybe this one I got it wrong or what? Let's see. Maybe we'll double check down. They have to be collinear, so the point is 3, 8. So it looks like something is wrong. Let's see which one is wrong. -3 is -7. 1. We have 1. Function f is at 5. It's good. This is at 0. That's 5. So 1. 5. That's correct. 7 is for the function f. Maybe we read it differently than for this one too. Let's see. Maybe I was looking at 2 for the other one too. Yes, it's 9 and not 7. See, I was looking at 2 to begin with. So let's put this one 2 here. And then we're going to do the 3 1 together again, okay? So 2 was at 7. And then I read -1. Yeah, I was looking at 2 when you said 3. 2 8. We're going to leave it alone and we can do the 3 1 together. And I will look at 3 this time. So 3. I don't know who noticed this one, but you're the one that's going to guide us to this this one for number 3. Because this one we're going to do, you're going to do it by yourselves. So first value we need for f of x at 3. Anybody can jump in?
Would
and
it be
help.
9?
One more time.
It'd be 9.
9, that's right. Okay, 9. And now we need g at 3.
-2.
-2. And now we need f minus g.
Be 11.
The point is 3, 11. B and 11. Okay, so now again, we check, make sure that all of them are on the same line, because again, you'll notice right away, if it's not, then something is wrong. You can easily figure out which one. And then we have our line. So this is the function f minus g of x. It doesn't have a name. They just left it as an operation. And the other graph, we can name it f plus g of x. And we're going to do one more with times the quadratic, so you can see how it's going to change into a quadratic function, the parabola. So f times g, so let's set up our table. Somebody's, I think maybe, let's see whose microphone is on and we can hear the movement on the table there. Let's turn up our microphones when we're not speaking, so we have a good audio. So x, f of x, g of x, f times g, and then point. Now for these ones, if you're choosing really small values for x, you're going to end up with high values for y and then very, very low values for y here. Multiplication of those values would be a big number that you really don't have in the image that you're given for the graphs. So you can definitely go through them, and then you notice that a number is big, you don't choose in the same location, you keep going. I usually always go from left to right with my choices, so I have nice continuous points in order, but it's really up to you. I would start again with a -4. We already have the value for -4, and we know the process now, right? So -4 is right there. This is why it's nice to have, again, the ruler. You saw me moving from 3 to 2 very easily. -4 keeps you aligned, so you don't read at a different value. So we need f at -4. We said it's 5, and the other one was -5. So you can see when I do 5 times -5, we're getting -25. So next point is 4, -25. I can't graph it, at -4, -25 is somewhere down here. Let's try -3. -3 f of x is negative. Did I switch these ones? F of x was -5, right? -3 is f of x at -3 and g of x at 4. -3 times 4 is -12. 3, -12. Can we fit -12? Well, this one is a bit closer, so I could put it somewhere here, like approximately there. But I still should move further to the right. So -2. F of -2 is -1. G of -2 is 3. -1 times 3, -3. So -2, -3. -2, -3, there it is. -1, f of -1 is 1. G of -1 is 2. 1 times 2 is 2. -1, 2. Our next point. Zero. F at 0 is 3, G at 0 is 1. 3 times 1 is 3. So 0, 3. One. F at 1 is 5. G at 1 is 0. So 5 times 0. 5 times 0 is 0. So 1, 0. Two. F at 2 is 7. G at 2 is -1. 7 times -1 is -7. So 2, -7. And I can already see the shape of the parabola, shaping it up. So how do I know it's a parabola? Well, I did a linear times a linear. Imagine x times x, whatever other things are around. It doesn't really matter for us in terms of what kind of function we're getting. So I know I'll get a quadratic, okay? Now you can even go further than this. You can imagine what kind of quadratic are you gonna get. Is it smiling parabola or frowning parabola? So positive leading coefficient or negative leading coefficient? Well, you can look at your lines. F of x is an increasing line from quadrant 3 to quadrant 1. So that would be a positive leading coefficient. And then g of x is decreasing from quadrant 2 to quadrant 4, and now it's going to be a negative leading coefficient. Then imagine the positive and the negative sitting in front of your x terms. When you're multiplying, your x squared term will have a negative in front of it, right? So a negative leading coefficient parabola would be a frowning parabola. Now, when I unite these points, I want to make sure I'm getting the shape of a parabola. Now, this one doesn't look like it's the vertex, so I'll just go like that. The vertex a little bit more to the left. And try your best to make it symmetrical. The more points you get, the better the drawing of your sketch will be. I mean, I wouldn't take anything that's nice. It's not nice to read. So you can see I went from point to point that was in the corner of a square. So I didn't choose 0.5, for example, because I would have to estimate that. I would have to estimate that. So it's just easier values to work with.
I guess if it was a bigger graph, it would kind of like spread out more, right?
What do you mean bigger graph?
Because since our points are all like right next to one another,
Mhm.
compressing it, like it's really kind of like a tight little parabola, right? But if your points were more spread out.
Well, yeah, I mean, depending on the orientation of your line. So if this is a steep line, if it will be like this, you get different points, right? So this one will be like with the less of a slope, also you'll get different points. So depending on the values of the y's for these functions, you get a wider or a narrower parabola, right? This has a higher, like if your line is really steep, the leading coefficient of that, it's the slope of this line. So it's a higher value. And this one also is pretty steep, you know, and you also have a nice big number there. So that if you multiply those numbers, you're also going to get a really vertically stretched parabola, right? Because the number here in front is going to be bigger. It's not going to be 1, you know, which is your normal parabola. It's going to be times something else, right? So it's narrower. Make sense?
Yeah, it makes sense.
So you can get questions like these when the graphs are given to you, like example 3. But you can also get questions like these when the graphs are not given to you and you would have to get the graphs yourself. So given the functions, f of x is x squared minus 3. So that's a parabola, quadratic, and the g of x is negative 2x plus 1. That's a linear function. Sketch f of x and g of x on the same system of axes. So you're going to sketch it over here. Basically, you're setting up the question the same way example 3 was set up. So we're going to put those graphs on the Cartesian plane. And then we're going to sketch the new function, which is g minus f of x. Now, attention at the order, okay? For that reason, I will first sketch g of x, so we have it in the right order. Now, g of x is a linear function. What's the easiest way to graph a linear function? To obtain the graph of a linear function. getting a couple of points, right? Now, I'm already thinking ahead and I know the points that I want. Okay, I want to choose points that have x's, the choices of my x coordinate, the same way I'm going to choose the x's for my quadratic. So I don't have to do the work double time. So I'm going to choose the -2, -1, 0, 1, and 2. Even though I don't need that many points, I will need it for part B when I'm going to sketch my new function. So for each of these x values, I will calculate the y with the table of values and I'll get some points for the new function, for the function g of x. It's not new. So -2, -2 times -2 is 4 plus 1 is 5. -1, -2 times -1 is 2 plus 1 is 3. And then 1 when x is 0. And then we have -2 plus 1, which is -1. And then we have -4 plus 1, which is -3. So those are the points: -2, 5, -1, 3, 0, 1, 1, -1, 2, -3. So let's go ahead and plot. -2, 5, -1, 3, 0, 1, 1, -1, 2, -3. Now f of x is a quadratic. Now, how can we graph the quadratic? Well, this one is quite simple because it only has the quadratic parent function and then subtract 3. So we just have to move every single one of the points of the parabola that we're so used to it, the 0, 0, 1, 1, 2, and 4, down 3, right? This is a vertical translation, 3 units down. So where will be those points? If you want, grab a pencil, if you have a pencil, and then erase it right after. So the parabola, that's x squared, was here. 0, 0, 1, 1, 2, 4, -1, 1, -2, and 4. Okay, and then just move them 3 down. There, I'm going to just actually use a pen. So this is 3 down. That's 3 down. That's 3 down. That's 3 down. And that's 3 down. And there they are. I'm just going to do my parabola through them. And I'm also going to continue here, the values of f of x. So for x is -2, I got the value at 1. When x was -1, the value is at -2. When x is 0, the value is at -3. When x is 1, the value is at -2. And when x is 2, the value is back at 1. Now, all I gotta do, since I've done my work cleverly, I don't have to combine them any other way than they're already there set up for me. There's my g of x, the y coordinates of the function g for the corresponding x, and the y coordinates of the function f for the corresponding x's. So all I gotta do is f, not f, g minus f, g minus f, working with the values that are in front of me in the table. So this answers part A. We graph the two functions. Now here we're doing already part B, right? Part B starts basically here with the prep that we've done in part A. Taking a moment here, you're not telling me to slow it down, but I feel like I probably should. Are you caught up?
I just need 30 seconds.
Yeah. I'll go and get a coffee refill. Everybody good?
Yeah.
Okay, so let's go then. G minus F. So because I have my G first, my F second, I don't have to sit there and flip them in my mind. Such an easy way to make a mistake. I don't know about you, but I need everything to be in the right order. Otherwise, I'll definitely make a mistake. So G minus F, 5 minus 1. 5 minus 1 equals 4. So we have our first point, -2, 4. See if I have a different color here for you guys that's visible. -2, -2, and 4. Yeah, it's pretty visible. And then 3 subtract -2. 3 minus -2 is 5. So -1, 5. -1, 5. Now here we're doing f of x, which is quadratic, minus g of x. What kind of parabola are we going to get? The other way around. G of x minus f of x. What kind of parabola? So we have a negative leading coefficient linear function, and we're going to subtract a positive leading coefficient quadratic. What are we going to get? Let's keep going. 1 subtract -3. We get 4. So 1, 4. Zero, 4, not 1, 4, 0, 4. 0, 4. You can already see what we're going to get. And then -1 subtract -2. We get 1. So 1, 1. 1, 1. -3 minus 1, -4. 2, -4. So we're going to get, because this negatives is in front of a positive, the quadratic term is going to have a negative leading coefficient. So you're going to get an upside down parabola. Okay, so break time. Let's see, what time is it? 2:42. So let's go to 3 p.m. 3 p.m. So go over your turn 3.1? Oh, somebody's here. My cat is here. What are you doing, silly butt? What are you doing? Just post. Okay. Okay, stop the share. Where am I? There we go. So function operations focus on domain and range of these new functions. Domain and range are part of the definitions of the characteristics of functions. So we can find out domain and range from the function's equation if we know the equation, or from the function's graph. Either or, you should be able to figure out domain and range. So from the equation or from the function's graph. Because the equation is the algebraic representation of the definition of the function, and the graph is the graphical representation of the function that you're talking about. Now, as a summary of these domain and range notes, we can group them into polynomial functions, and we'll discuss again the domain and range of them and how they're particular to some of them. And then we're going to go to square root functions because these ones have some restrictions, and also to the quotient functions because those ones also have some restrictions. Now, for polynomial functions, domain is going to be always the real numbers for all kinds. So it doesn't matter if it's odd degree or even degree. So odd degree like linear, cubic, and quintic. All of them have all of the real numbers, and also for the even, for quadratic and quartic. They're going to be all the real numbers. Now for the odd degree, linear, cubic, quintic, the range is also all of the real numbers. For even degree, because you have a max or a minimum, the range will be less than equal to the maximum slash bigger than equal to the minimum, in that order, with a slash in between, okay? So depending on where that maximum is, the minimum is, you'll have either less than equal to or bigger than equal to, okay? And that's for both quadratic. So quadratic will have either a minimum or a maximum. A quartic can have also a maximum somewhere, a minimum somewhere, right? So depending on those, you may have your range differently. Let's review. And if we have to work with these functions, we can think about their domain and range accordingly. Now, sometimes we're going to have to work with square root functions. And since we haven't discussed this function separately, we only discussed it as a parent function. We want to remember that the domain of this function is restricted. We already talked about the swoosh graph, right? And we said that we can only take x's, right, as large as 0 or more, right? We cannot take them smaller than that because it doesn't make sense. But in some situations, when you're going to work with a given function that's a square root function, you already have other things under it, not only x itself, but x minus 1, so or an entire expression. Now, when you plug in x's here, the expression changes depending on the x you're entering. So what you want to make sure you have when you figure out the domain of these new functions under the square root, that whatever the function is, let's call it f of x, that function f of x is going to be bigger and equal to 0. That's going to be the condition. And whatever that value will end up to be, the range can be concluded for it as well. Now, how do you figure this one out? Let's say let's use this example. Well, f of x in this example is x minus 1, because if you look at these two notations, the square root is over f of x entirely. So over this entire expression, that's f of x. Now what you want to make sure this is bigger and equal to 0. So x minus 1 bigger and equal to 0. You're solving it just like an equation. So you move the -1 on the other side. And you found what x should be. X must be bigger and equal to 1 for this to work. So now check it. 1 minus 1, I get 0. It works because I can take square root of 0. If I take something less than 1, let's say 0, if I put 0 here, 0 minus 1, I get -1. I cannot take a square root of that, so it doesn't work. That's the domain of this example. All my x's have to be bigger and equal to 1. Now, if my x is bigger and equal to 1, what's going to be my y? The smallest y that I can take. Well, all I have to do is plug in 1 minus 1, 0, so the y is going to be 0. So everything is going to be larger than 0 for the range. For quotient functions, and this is actually something that we will do, part of function operation, sometimes you'll have to do a quotient of functions. The domain has to be, you have to be careful that this q of x that comes from the quotient, from the division, cannot be 0. Well, why? Because we cannot divide by 0. Example. So let's say we have q of x as x minus 1. Let's say f of x is 3x. So then our function y will be 3x over x minus 1, like that. You divide. Now this cannot be 0. You just write that down. X minus 1 cannot be 0. All right. And you just solve for it the same way we've done here. So x cannot be 1. Now in this situation, the domain is all of the real numbers except for this value. So it's only one value taken out, not an entire range or interval of values, like in the previous example. Sometimes you have to combine them. Sometimes you have to combine the conditions because you may end up with something like this. Y equal square root of x minus 1 over x minus 1. Well, one condition comes from here, right? Because of the quotient, I cannot have division by 0, so I have to exclude number 1 from the domain of the function y. And then the other condition comes from here because I have a square root. So that gave me x is bigger and equal to 1. X is bigger and equal to 1 from that condition. Now, if I combine them, because I have to, it's for the function y, they both have to be satisfied at the same time. What do you think the condition would be? The combination between these two.
X has to be bigger than 1.
That's right. Good job. So if you combine that, you say x is bigger and equal to 1, and then you say not 1, that means obviously x has to be strictly bigger than 1. So in some situation, you gotta do both, okay? You have to think about all of the possibilities that's not gonna let that function exist. And you have to exclude them from the domain of the function. So let's do some more examples. given f of x is x plus 2 squared minus 5 and g of x is 3x minus 4, determine the equation of f of g of f times g of x and then domain of h of x. So this one we've done already, equations. All we gotta do now is also figure out the domain of h of x. So h of x is f of x times g of x. F of x is x plus 2 squared minus 5. Let me put an extra set of brackets because I'm going to times it by 3x minus 4. This is very algebraic, so we're going to have to do quite a bit of work before we get to the final equation. So first, the squaring. This is already written in standard form, for example, for graphing purposes. We don't need it. We just need the actual equation. So we can open up that bracket, the x plus 2, everything squared. So we will get x squared plus 4x plus 4, and then minus 5. Don't forget that one. I'm just going to copy the other binomial times 3x minus 4. Here I have like terms, so I'll put those together. So I'll get x squared plus 4x minus 1, and then times 3x minus 4. Now we have a trinomial times a binomial. Distribution has to happen for each of these terms of the trinomial with each of the terms of the binomial. So we have x squared times 3x is 3x cubed. X squared times negative 4 is negative 4x squared. Then the next one, 4x times 3x is 12x squared. 4x times negative 4 is negative 16x. And then negative 1 times 3x is negative 3x. Negative 1 times negative 4 is positive 4. We're going to put the like terms together. Three x cubed, positive 8x squared, negative 19x plus 4. It's a cubic function, therefore the domain is all of the real numbers. Consider the function f of x equals x squared plus x minus 6 and g of x 2x plus 6. Find the equation of the function g divided by f of x, find the domain, and then the k of x, which is upside down, and then find the domain. So let's see, h of x first is g of x 2x plus 6, and then f of x is x squared plus x minus 6. Now, the equation is this, and it can stay like that, but what if it says explicit or the most simplified equation? In that sense, you would have to see if you can cancel some of this, some of the common factors out or not. Not the x from here with the x's from here. That's a very big mistake that a lot of students are making. Remember, you can only cancel top, bottom, or diagonally if there are things that are multiplied, okay? So for that reason, before I can get to the domain, I would factor anything that I can. At the top, since it's a binomial linear kind, I can only factor out the 2. So 2 in front and in bracket x plus 3. So that's a simple GCF factoring. At the bottom, I can factor the quadratic, or at least I can try to factor it using the shortcut method, because in front of the x squared term is number 1, right? So that means if I find 2 factors of -6 that add up to +1, I already found my 2 binomial factors. So I just need these 2 numbers and I'll just plot them right there. So what are 2 numbers that multiplied give us -6 and added give us +1 from here?
Three times -2.
Yeah, 3 and -2. If I times them, I get -6. If I add them, I get +1. So these are the numbers, the factors that I'm looking for. So we just put them here. So +3, -2. Now we can see that the common factor is x plus 3. The entire bracket is a common factor. So we are ending up with 2 over x minus 2. That's the most simplified form of h of x. Not that one, but that one, right? Now we need the domain of the function. Remember what we said, the domain of the function when you have a quotient says that the entire expression at the bottom, not this one that's already simplified, the one that you start with, okay, the f of x, we have to put the condition that it cannot be 0, okay? So the domain will come from x squared plus x minus 6 cannot be 0. That's just like solving an equation. It's a quadratic, and I already know I can solve a quadratic by factoring. So I have x plus 3 times x minus 2 cannot be 0. And then I can see what the x's are, and I cannot have in my domain. X cannot be, and x cannot be. X cannot be -3 from the first bracket, and x cannot be 2 from the second bracket. Everything else I'm allowed to have for this to exist. So all of the real numbers are okay, except for these 2. K of x is the other way around with the f at the top. So we have x squared plus x minus 6 at the top, and then g of x at the bottom, 2x plus 6. I would approach it exactly the same way, even if the functions will be different. I would want to see if I can factor them so I can see if anything cancels out. So we already know that's x plus 3 and x minus 2 because we've done the work in the previous question. And we already see the cancellation. We end up with x minus 2 divided by 2, or x over 2 minus 1. It's like variations of these. There's a bunch of them. Now the domain. The domain for this new function k of x comes from putting a condition on the denominator. So the 2x plus 6 cannot be 0 because I cannot divide by 0. So I have to exclude that. But what is that x that's going to make the denominator 0? I have to solve this. So 2x cannot be -6. Divide by 2, divide by 2. X cannot be -3. And again, all of the other real numbers are accepted just not this one. These two, when you write that equation, this has to come with that exclusion. You here again? Let you finish up. If there's any questions, you let me know before I move on. So we just ended now the domain and range. Now this last part of your notes refers to a new way of getting new function, is the idea of composing functions. So two functions that are combined in a certain way that I'm going to teach you today how to. They're called composite functions. And the operation is called composition of function. Composition of functions. Okay. Composition of functions or composite functions are formed from two other functions in which the outcome of one of them will be the use, or it will be used as the input of the other. Outcome, output, same thing. So if we're considering two separate functions, f of x and g of x, and we want to compose them, so we want to do compositions of function to get this new function h, the notation is going to be f of x composed. It's not a dot like times, it's a circle. And the way we write it is f of g of x. So this is the output of the function g of x is the y, and becomes the input of the function f. The way we explain it in the first sentence there. The way we read it is f of g of x, or f at g of x, or f composed with g. Now order matters for these ones too. So if I say f of g of x, the output of g is going to become the input of f. If I say g of f of x, then the output of f becomes the input of g. So very, very important to note that they are not the same. So order will matter. So let's start with some equations. F of x is 4x, g of x is x plus 6, h of x is square root of 3x minus 1. We're going to go through doing composition for these four types of questions. So first is f composed with g of x. I like to write it f of then g of x. It's very easy then to recognize what's the input of what. So now, if g of x is the input of the function f, let's rewrite it as f of, and replace the x part of f of x with the function g of x. So x plus 6. And now you're going to think of this input. the x plus 6, as instead of everywhere you see x's in the function f of x, because you replace this x with x plus 6. So you're going to replace here x plus 6 4 times x plus 6, so it's 4x plus 24. Done. Let's do the opposite to the g of f of x. So g of f of x is 4x. So everywhere you see x in the function g, the x plus 6, right there, you're going to replace it with 4x. So it's going to be something plus 6, but not x anymore, the new input, 4x. And we're done with this one, 4x plus 6. H of f of x. H is the function square rooting, right? So h of f of x is 4x. So the function h is square rooting. Everywhere you see an x, you're going to replace with 4x. So square root 3 of 4x, plug that in, minus 1. So square root of 12x minus 1. G of h of x, g of square root of 3x minus 1. The function g is x plus 6, so x plus 6. The x is square root of 3x minus 1. Done. Function values. So we're doing exactly the same thing we've done for function operations, for composition of functions. First, we went through equations. Now we're going to function values. Remember, these are the y values. Now with composition of functions, you got to be careful because the input of one of the new function is actually the output of the other one, right? So we have to be always careful of that definition. Output becomes input. If I have to work through the function value of the composition h composed with g, so h of g of 3, if I write it like that, it's a bit more clear. What I have to first evaluate g at 3 and get the y value, and that y value becomes the x value of the function h. So this is y, okay? So let's see, h of, what's g at 3? 3 plus 6, right? So we do h of 9, okay? Now this 9 is the y value of the function g when x is 3, right? So for the function g, we have that point, 3, 9, and we found this 9 through this work here. Now for the function h, we have a new input, output of the function g, which is 9. And I have to go to that work. Plug in 9 everywhere I see x in the function h. So 9 f squared. So 81. What's the new function point? The new point is going to be starting with the x, so the x that you started with 3, and ending with the y of 81. Okay, let's go to the next one. F compose of h. So f of h of 4. F of h of 4 is 4 squared, so f of 16. And then we just do 4 times 16 for the function f. 64. G of h at -2, g of -2 squared, so g of 4. 4 plus 6 is 10. How's everyone doing? Are you all caught up?
Yep.
The next part would be to work with graphs. So how to get the composite graphs. Sketch the graph of f compose with g of x. Let's name it h of x. So f compose with g of x in that order. I always like to write it f of g of x. Now, because I need g of x to actually figure out f of that, in your table, you want to write that one first. And then f of g of x comes as the next column. And in the end, that's going to be h of x already. So you're not going to have as many columns as with operations of functions. So this is how you're going to set up your table for these ones. Your first one is going to be x. The second is going to be g of x. The third one is going to be already f of g of x. And then the point. It's only 4. Let's do some rows because this one usually takes a while because your ruler doesn't stay in the same spot. We're going to remember the definition. The output of one function becomes the input of another. So they don't have the same input, the functions f and g. Okay, we're going to change it because of composition. Now the x we choose is going to be the x of our points. Okay, so that one doesn't change. Whatever I choose here, I'm going to put here. So for example, I'm going to do the first couple of them by myself. The same graphs I'm using, because I don't have that many graphs to show work. So you'll have them, most of them, in your practice questions. So -4, I'm choosing. So if I choose -4 here, I'm going to have -4 here, my point. Okay. Now the difficulty is in the middle. For the g of x is not hard because g of x, it's a point that I'm reading with the y at 5. So I'm putting 5. The next one, though, follows straight into f of. So I'm not doing f of -4 anymore. So I'm not reading it from the next point. I have to do f of 5. So that means now my ruler has to move at 5 and read the function value of f at 5, which is 13. 13. So now the point is -4, 13. Okay, let's do one more. Let's choose -2. The first one you can read for g of x. Right there, the y is 3. But then you have to plug it in as being the new input of the function f. So f at 3. So you're not at 2 anymore, -2 anymore. You're going to be at 3. So f at 3 is 9. 3, 9. So our point is -2, 9. Now let's analyze it a little bit for the expected graph, so we know how many points we should keep going and working with. You're going to have a linear inputted in another linear. So linear composed with linear. What do you think you're going to get? Think about an example.
Linear?
That's right, you're going to get a linear. Because think about an example. If you have 3x composed with x plus 1, right, like that. The x plus 1 becomes the new input over here. So basically you have 3 times x plus 1. It's still going to be a linear function, okay? Not going to change. So you can always analyze it. If you're not picturing it, just give yourself an example. You can picture it right away. So we're still going to get a linear. Let's keep going and make sure everybody understands how to get these values. Who wants to pick the next x? And then we're gonna work toward. Don't be afraid. If you're scared of them because it's hard, you be the one that says a number right now, so I can make you figure it out. These values. Make sure that you're okay with them. Let's see who's not quite getting it. This is the time.
Six.
Did you say 6?
Yes.
Okay, 6. 6 for g of x. What is going to be? So you want g of 6.
$15.
This is g, the function g.
$5.
-5, right? -5. Okay, first one good. Now, the next we're going to do is f of -5, which is You move the ruler, you were at 6. Now you're gonna move at -5. F at -5. That's the point. It's the y.
7.
But with -7. These are all negatives, and those are all positives, right? So -7. Now the final point will be 6.
6, -7.
That's right. 6, -7. Good job. Somebody else.
Two.
2. Okay, let's do it. 2. G at 2.
-1.
-1. Good. Then
-1. Wait,
of -1.
hold on a second. Sorry, 1.
1. And the point is
2, 1.
2, 1. Okay. Good work. Anybody else wants to try it?
Four.
4. Okay, let's do 4. So the first step is G of 4.
Okay. 4. -3.
-3.
Then f of -3 equals would it be -3 or
Now you go to -3 and then you read the y. -3. So the point is
4 -3?
for -3. Now, if we made any mistakes here and I wasn't paying attention, all these points will end up linear, because if it's a linear function, they all have to be straight on a line, right? We call that collinear. So let's do that. Let's see before we move further. -4, 13. -4, 13, somewhere there. And then we have -2, 9. 6, -7. Let's see. So far, so good. Let's see. 2, 1. Four, -3. So far, so good. Right? So they're all on the same line. Does anybody else wants to try these ones? The composition? Because it is a little bit different than, I would say a little bit harder than operations of functions.
8.
8. Okay, let's do 8. So the first would be
G of 8.
yeah, G of 8, which is
7.
-7.
Oh, I heard. Oh, yeah. Then I have -7 equals
Somebody's at the door. And we got. Anybody else wants to try another one? Okay. So this is it. Your photocopying might not see the little lines for the quad paper. So you can just give yourself some lines with a ruler here and a pencil. So you have an easier time finding the values. This is not a really good, it doesn't pick up the lines when you photocopy it. Okay, so this is it for lesson 3, everyone. You can use the next 10 minutes or so for a break.